Hello and welcome to a continuation of my video series which looks at using items within the proto-pic Arduino Starter Kit. And today's item in particular will be the DS1302 Real Time Clock that comes with that kit. So I hope you'll enjoy today's video and learn something from it. A quick overview. First of all, this video assumes that you have a basic understanding at least of functions, structures and pointers in Arduino C++. Now the last two items, structure and pointers, you may find a little bit more trickier or a little bit more advanced, but I cover that in an earlier proto-pic video. So hopefully you'll either have enough background to this or there'll be enough explanation within my video for you to follow what I'm doing. Now first of all is a little note about this Arduino compatible project starter kit from proto-pic. Now essentially is this starter kit, which contains many items which you'll find in other starter kits, contains items that we'll be using, things like LEDs, resistors, cables and an active buzzer to do beeping noises, and most importantly for this project, a real-time clock. So if we close that down just now, is the focus, as you can imagine, is going to be on using this real-time clock that comes with the kit. Now with a clock we need to be able to set date and time, because this clock not only does time but it does date as well. And we can set that at either design when we're writing the program or at runtime, and this can be done by both in today's project. Now the runtime setting can be done either via manually typing in a string of characters into the serial monitor, and the program will then decipher that and make the settings on the real-time clock so it gets an idea of what the time is we want to set it to. Or, and this I think is a very useful mechanism that can be used by you many times if you use other programming languages in particular, that we can do automatic serial input via a PC program, which is a lot less hard work. Now in addition is a real-time clock. Like many of the items we find in starter kits or any kind of kits, can be very complex electronic devices, and these electronic devices have data sheets, and sometimes you've got to be a real expert to be able to understand what it means by it. Luckily there's a lot of experts out there, some boffins, who are very happy to give their time freely, and they sit down and study these data sheets and produce tools that ordinary people, certainly I'm talking about myself here, can use without understanding and going over all the technical details. So this program also demonstrates and shows how to access and utilize third-party tools which are available on the internet. Now one of those tools is going to be for directly using the real-time clock easier, but another one is just really for ease of use. And one of those tools allows us to use C++ output streams, which essentially replaces the need to have parts 3 or 4 serial.ln statements in Arduino IDE and replaces them all with one. And also is that having this program will allow us to move on in our studies in a future video. And one of the things I would like to do is to be able to add liquid crystal clock displays, which are also in the proto-pic kit, and so that we can actually see the time. So hopefully that's what we're getting through today, and I hope that you understand and enjoy it. So now you've got a rough idea of what this video is about to do. Here's how I decide to split it up. First of all, we'll have a circuit diagram, and then an explanation of how to get these library files I talked about for real-time clock and for various tools, and the mechanism I hope that we do it by, hopefully be able to use in all your programs. Then very importantly I think, and where the most of the bulk of the time is spent, is by looking at the overall program structure and understanding the coding that I've done. And then finally we'll look at linking to a PC using this runtime changing of times, and the language I'm using is one that's C#, but almost any language can be used within the Visual Studio environment, which is a separate program from the IDE. Right, here's the circuit diagram. Now first of all we'll notice that it's got an Arduino Uno on the left here, and it's got the breadboard that comes with the kit on the right. Both these come with the kit. And on the breadboard we have two main items, an LED which will flash depending on what the hour struck is, and an active buzzer. Now diagrammatically I've drawn the active buzzer like that, but in practice it looks something like that. Now we can see that one lead on the active buzzer is longer than the other. You can see that that one is connected via this green wire, it doesn't have to be green of course, to pin 11 of the Arduino Uno. So essentially an active buzzer works by when we set that port high or that bit high, then the active buzzer will make a sound. When we set it low, it stops making a sound. Now the LED is connected into, you can see here just these two important things are the rails, or the power rails. We've got the red line here, which is connected to the 5-volt system, and all the way along this line here that's going to be equivalent to linking to the 5-volt. So we can see is that we've got the real-time clock connected to that, and the real-time clock has VCC and ground clearly marked on the display. So that goes to the +5, that goes to the ground. Now it's got 3 further lines, clock, data and reset, and these are connected as we see via this code here. This is code that we would have within the actual IDE itself, the program itself, is that the clock is connected to pin 6 here, that the data is connected to pin 7 and the reset to pin 8. So we can see there this is stuff that's within the program, and we have the LED pin connected here to pin 11, to pin 12, sorry, that's pin 12, and we have the buzzer connected to pin 11. So there's the manifest constants, the hash defines within our program, which link this real life linking to there. A little word on this stuff here is that we see a battery in here. It's a little button cell battery. Now notice that's not supplied with a kit. proto-pic can't actually ship these things. You have to require other vendors to do so. I don't know why that is, but that's just the way of life. So we have here the red LED. Just a matter of interest on the LED is these LEDs, when they come out of the kit, have 2 legs. One is longer than the other. The longer one is the anode, which is connected to via the positive. In this case, it's connected to this port via this resistor. I show here a 330 ohm resistor, but in fact, the kit supplies 220 ohms, which are perfectly fine for that. If the legs have been trimmed, so they're both the same size, is that we can notice is that the outer casing of the LED has a flat area on it, and that flat area is actually connected to the cathode. So there's a circuit diagram, and that should be enough for you to get your job done. Now here's how we get the library files we'll be using within this program. Now the first library file we're going to look at is for the streaming, this one that allows us to use a serial monitor to output information, and sometimes a more elegant way than the inbuilt Arduino one of using serial.print and serial.println. So within the program we would use it by using a hash include at the top of our program, so hash include streaming.h. And to get that to come in, is the first thing we have to do is to find the zip file where the tools, which include streaming.h and other things, the tools are to be found. So first of all, we'll use Google or a friendly browser to search engine to look for this. So if you look for streaming5.zip on Google or something, the first thing that comes up with is a number of links. The one I picked was right at the beginning, a guy called Gene Reeves, Arduino Streaming, and by looking around at that code there, I was able to open a zip file, open or save a zip file, and there's the name of the zip file. That's the one we'll look for. Essentially what you would do is choose the save option, save it to a location using File Explorer on your browser, on your PC, and take note of that location. Now when you want to actually use this within your Arduino program, Arduino sketch that you're going to make, is go to Sketch, include library, and add zip library. Then you'll be given a facility to then browse via Explorer. If you browse to that file that you've just saved, that's why it's important to remember where it is, and click it, then the Arduino IDE will do the rest for you. So, and it will add that hash include to your program as well. So that allows you to use the tool that I said is fine, but you also need to use the real-time clock. And the include file I use for this is that's a header file that simply has within it commands which make be able to use the tool more easily. So if we Google for this header file, it will come up with a link somewhere, and
one of the links I chose was one of the early ones, and this was a GitHub one by this gentleman called Chris Fryer. Thank you, Chris, for all your work. And also as well, thank you, Mr. Rees, or Miss Rees. So when we get this library here, then again we'll get an option somewhere to either open or save the zip file. Again, take the save option, save that zip file to a known place on your PC, and use this again so it adds to go to hash include library, add zip, and everything's taken care of. So that's essentially how we get and use the library files. Right, let's have a quick look at the overall program structure, and then we can dive more deeply into it. Now, first of all, the three areas at the top are pretty much what you'd have with any Arduino sketch program. We have the global area, in which we put information and data that we want to be able to use throughout the program. Then we have something called setup, which is a function, and that setup is run once as we run a program. And then we have this kind of master loop here, which goes round and round doing stuff, sometimes hundreds, possibly thousands of times a second. And some of the tools that we have within here is that I've got 1, 2, 3, 4, 5, 6 additional functions other than setup and loop that are used for various tools, facilities. So 1, check for time reset, and you can read what I've got here. And the program, the rest of our description of the program will look at just these bits. So first of all is, let's look at the globals. So here's our global area, and essentially this is the part of our sketch that comes before the startup, or the setup function. So first of all, we've got a couple of hash includes. This will allow us to use effectively and properly the libraries that we brought in earlier, the streaming library and the virtual robotics real time clock library. And here we've got hash defines here. These are instructions to a thing called the preprocessor, which before it compiles the code will look at our actual text and seek to replace any values that we define. So that hash defined clock is 6 is, we'll see here that I've got the word CLK. Again, the case is important, capital C, not as lowercase. CLK is that before this is compiled, is it will replace that value CLK with 6, data with 7, RST with 8. We saw these values in our circuit diagram. So this line here basically says you've got that real-time clock tool that we've defined with up here, then create for me a variable called myRTC, send these values to it, parameters, that links up the pins, and then I'll be using that within my program. So this RTC object will be referred to in my program as myRTC. And because I've written this in the global area, it means that every part of the program will know about the existence of the myRTC variable, and it will respond to it. Now, also as well, just in terms of sheer use, when I run my program, I mentioned earlier that we can set the time at design time, and a common place might be is what happens if there is no time set on my real-time clock. Well, essentially what it says is that if you might want to set the time, date and time in the startup. So here I've got a line that says hash define set RTC in startup, which means if I've commented it out, then this will not be visible. It means that within the startup function, I can actually check to see whether or not I want to use this as code. We'll see that when we come to startup. Now also as well is I didn't want to have the time printed out every second or all the time that it went through the loop. So here I said is basically print out the time on the serial monitor no more than once every 5 seconds. Now then down here is I found is that because I'm dealing with sending lots of values in a date time, we've got the hours, the minutes, the day of the weeks, the years, etc., is that sometimes I want to be able to wrap up the information within a date time into one place, and that's where I've created a structure myself here. Essentially what I've done is I've created almost a new data type, instead call it date time, which means that later on I can refer to using this particular construct just by the name date time. So dt then, although it's only one thing here, it means that that one thing can have all these values and elements individually referable, which is a good way to package the information within a date time. And this information here is actually, these are called fields, and these fields here, these fields then, I've chosen to have the smallest possible data type, to try and save space later on, for the information it's likely to contain. So for example, a byte even, can be in an unsigned or a signed form. Even if it's in signed, means it's got a plus and minus, is that it can have a value up to +127. If it's not signed, it can have a value from up to 255. But here essentially, day of month, never more than 31, never more than 12. Well, and a year of course can be, at the moment, unless we get to the year 65,536, an integer will do fine. But I don't plan to be around by that year, so it doesn't really matter anyway. Hour, 24 minutes, seconds. Weekday number is important. When we put a date and time in, sometimes we want to know that it's a Thursday or a Sunday or a Monday or a Tuesday or whatever. So the weekday number is, by convention, has Sunday as the day 0, Monday as day 1, Tuesday and so on. So the weekday number tells us what day, tells our real-time clock program what day the week is. Here as well is, I wanted to show is that we could actually have not just members fields that had values, but we can also have functions within a structure. And I've got one here called isLeap. It returns bool, which is a true or false. And essentially is what it does is it first of all looks, says that that is year. Now year, remember, is accessible to it because it's there. So it basically is saying is if the year that if the year that I've got in here is exactly divisible by 100, that's what that means. If I can divide it by like 1900, 2000, 2100 or whatever, then I'll treat it as a century year. That's this information here. And if it's not a century year, then do this stuff. Now the reason I've done that, and again, not a lot of people actually know this, not everyone knows this certainly, I know that from experience, is that if we have a century year, it has to be divisible not by 4 but by 400. If it's not divisible by 400, that century year is not a leap year. So for example, 1900 was not divisible by 400 exactly, so 1900 was not a leap year, even though 1900 is divisible by 4. When it comes to 2100, we're back to the cases. 2100 is not divisible by 400, so it's not a leap year either. And one of the things I wanted to do was to find out whether we might have a problem, let's say something like 80 odd years from now. Not that it really bother me, but I thought I would work it out anyway. But essentially, as this code here says, if it's a century year, then it's got to be divisible by 400 to be a leap year, otherwise it's not a leap year. If it's not a century year, then all it has to do is be divisible by 4, in which case it's a leap year. And there's the structure definition. Now also as well, finally here, this bit here, int current hour 24, is when the program comes in. When the program comes in, I want to be able to check current hour 24. So here is I'm declaring it. I'm not giving it a value. It'll be 0. It'll just be take the default value for an integer, which is 0. But later on within startup, we'll be looking at the value of the current hour. This will allow it later on to determine whether or not the current hour has changed. So I might want to have beeps. So that's basically our global area. Okay, here's the setup function. First couple of lines here, pin modes. I'm basically saying is that I'm going to have this LED pin and buzzer pin set to be outputs, so that the lights can go on and off, and the buzzer can make a noise or go quiet. And I'll call that a chime. Now and then I say serial.begin 9600. Again, I've chosen 9600 as just because of habit. In fact, because I'm doing a lot of serial communication, it might have been better for me to have a much higher value, but we could worry about changing that later. But when I do this serial.begin, I need a command which actually will sit around and wait until that serial is ready. Otherwise, at the beginning of a program, we might get some funny information on our serial monitor. So essentially what I would do here is do this line of code here, these lines of code here, while, and then that says not serial. While the serial is not ready, and we have code in here, I could, now that will be a wait, but it should make sure that pretty much all the serial output we get will be sensible, rather than starting halfway along. Now, I've also got another form that you might see sometimes of that while serial. This waits until the serial is ready, but this line here, if for example we're waiting for some serial command, serial information to arrive, let's say from an external program, we might want to use this format if while not serial available. But if we have that and we don't have any information going in, then it's going to sit around forever basically. It's going to sit around for a long time anyway, until so we can choose. This is what I'm choosing because I'm only waiting for it to be ready. This I would choose if I'm waiting to get some information, say from an external source like a PC. Now remember we had this manifest constant set RTC in startup. If I've commented it out, then this will not do anything. Essentially is what this do is that the compiler will just say, compiler won't even see that code if we've commented out that within our global area. But if we haven't commented out, then here what I've got is I'm creating a variable of type datetime called dt, and I'm calling a function within my program called parse RTC in buffer. What it is it's a string of information which contains the date, a space, the time, a space, and the day of the week number. Day of the week number 2, well, Sunday 0, so 1, 2 will be Tuesday. And this, what this does basically, it says, is I want you to take this sequence of characters, this string of characters, and I want you to parse it or break it down in some ways so that the values you've got in it fit into this single variable called dt. So that we'll have, for example, dt.month will be 9. What I'm doing here, of course, is it's UK version, so that's the day and that's the month rather than the American version. So basically is that at the end of this line is that dt will contain that information but put into the proper format for a date and time. Then this line here, my RTC, this is the variable that I created within the globals that essentially is got from it's an object, it's created from the class, the Real Time Clock class, and it's setting the time, and this is the order it expects it because dt.seconds, what it will do here is it will basically put in 40, then that will be 38, then that will be 12, and weekday number is going to be 2, and then day of month, which is 10, month and year. So these values get set, so at the end of that statement is that real-time clock should be set to that date. And here we're using that thing for the streaming Deutsch. Instead of having, say, serial.println, is I can have here serial and then these two less than signs. It will print out, is it a leap year? And then here it's printing out the year, which would be in this case 2019, and then a space, and then whether or not it's a leap year. And 2019 is not a leap year, but what to do, it's been informative, if you've got this point, you've got the program up to actually test it and put in different years, like put in things like 2100 and find out whether 2100 is a leap year. Well, because it's not divisible by 400, it won't be, but I think you might find is the real-time clock doesn't know this, so we have to be careful. It could be a little millennium, in this case a century bug in the making. But essentially, remember, is that code only runs if we've left this comment, this hash defined set RTC uncommented. Now, once that's done, then is I want to update the time. Updating the time basically says you set the time, and just now make sure is that all these different values are actually now up to date. So it makes sure that now the clock here, if it's run that code, will have these dates and times, but if it's been running itself happily on the battery, then this is at least finding out what it is. So do this before we really read it, is what I'm saying. And current hours 24, we declared that in the globals, is equal to that. And essentially it is later on when I'm running all my program, then if the hours change, then it means I might need to have chimes, so it might have times when looping. So now it's time to start looking at some of these functions that we've written outside the startup and loop. And the first one we've already looked at least we've looked at it in terms of what it does, is that essentially it receives a string. It receives a string of characters, and it then looks at the string of characters and passes or interprets them as being different values of a date. And notice here is that it says it needs a character pointer to something called buff, and that it also receives a pointer to a thing called DT. Now, if I go back here, if you recall from looking at my previous videos on structures and pointers, is that when I called parse RTC, it had a string constant in here. That string constant essentially is when we put a string constant or a character array constant in, it interprets this as being the address of where that position, the first character 1, is in memory. So essentially is that by writing that string in there and calling this, it's sending a pointer to the first character of that string, starting at the 1. And here, notice in fact I've got prefixing this with an ampersand, and an ampersand, if you may recall from a previous video, is ampersand says is the address operator. So what it basically is saying is, wherever you've gone and stuck DT here, wherever you've gone and stuck DT, I want you to put that in here. In other words, I want you to put the address of that so we know whereabout in memory it is. So essentially then is this first thing is it gets these two pointers, one a pointer to a string of characters and one a pointer to a date time structure. So going forward again back here, and that's what we say there. So essentially I've got some examples here, talked about UK format again, and I've put a date and time in just so you can look at that example at your leisure. Then essentially the rest of the program is the same. What it's done, it's looking at different parts of this buffer and it's extracting information and making them into actual integers or whatever, or values that is put into the structure. Because what I want to do is to look at all this, and I want to put 01 as the day of the month into this DT value, 08 as the month, and etc. Of course, and essentially is one of the things is it expects well formatted, so I don't just get a 1/8, I get an 01/8. And it's important is that when we format a string, we know exactly how it's formatted. If it does it have leading zeros, does it not? So essentially here is I'm creating a variable called DOM, and in here I'm saying char, so I'm creating a character array of 3 characters called ch3, and I'm setting it equal to double quotes AB double quotes. Now all I'm actually I don't need to actually put in any specific values. I don't have to put in A and B here. All I really want is that when we create a character array, I'm saying 3 characters, because although I've only got 2 here, this is meant to represent a string, and I want this to represent a string, and a string in C++ has at the end of it an extra character that we don't see. It's a character 0, and I don't mean the digit 0, I mean the actual value 0, which signifies the end of the string, as we remember from a previous video. So this essentially creates ch3 to be AB followed by a 0, which means it's going to be effectively a string of 3 characters. ch5 is going to have 5 characters. So but here I'm only using the 3. I'm saying is I want the first character of those 3 to be whatever value that buffer 0 is, which is buffer 0 is going to be the very first character, which is going to be, like in this case, it's going to be 0. So that 0 will go in there. But that 0 will be as a character. Then it says ch1, which is the second one. Remember, it starts at 0, 1, 2. So ch1, which is the second character, will be whatever value was. So at the end of this line, with that example, that's going to be the character 0, and that's going to be the character 1. So I now have basically a 2-byte buffer. 2-byte buffer. The extra byte, remember, was just for the 0 at the end. And here I'm saying is I want you to make the day of the month equal to, and here's an inbuilt function of the Arduino IDE called A2I, ASCII to integer. It's saying basically, give me something that's just the characters, like the ASCII characters, like 0 is what, 48, 1 is 49. Give me the values of these characters and convert them into an actual number rather than just a set of couple of symbols. So what this does, it takes 0, 1 and it makes it into the number 1. And now that the DOM at the end of this will have the value of 1. And here, this bit says because I sent a pointer, dt is a pointer to this, I use this dt and then this arrow notation. I'm just saying is go and now make the DOM field or member of the dt structure, go and put the value of DOM into it, which is the number 1. And then I do the same for months. I'm now taking CH3 of 0 is buff 3, which is 0, 1, 2, and then buff 3 will be that character 0 there. It's 0 in this case because I've done it as 0, 8, but of course it could be 1 as in 1, 2, or 1, 1, or in 1, 0. So it's important that we carefully and methodically go through each of these, counting its position, getting the index, and then we do the same thing. So we're converting, in this case we're converting this CH3, we're overwriting it essentially into a new value, and then we're using this A to Y function to get the month, and then we're putting the month value that we've just calculated into dt month. Now here, I've got this down here, this line here. If you remember from my video on structures and pointers, is that another way of writing this instead of our notation is to do what's called a dereferencing and then do dot one. So there's another way of writing that. It's the same thing. So this won't change anything here. It's just saying is make the month 8th. Now it's making it make the month 8th again, so it's going to say 8, but it's really just a reminder and it's for illustration purposes. So that's using the pointer or using the dereferencing. I think personally I prefer this, and most people I think do when they're using pointers to structures. And then I've got the year to work out. Now the year is a bit more complicated. We can see here is I've got to take those characters and extract into a buffer of a size 5. So I'll put 2 in the first one, 0 in the second, 1, 9, and then of course we don't forget that all important space at the ASCII 0 value at the end, which signifies the end of the string. So here is this now puts in the value 2019, and then instead of using and then as before we just use this ASCII to Y again. This time we're using CH5, so it will now take that and make it into the integer 2019. Then we do the same again. So essentially is going all the way along here. All I'm doing is I'm extracting character at a time from the right place the information within this string, put it into new strings using the ASCII to I function along with that like this new character buffer or string that we just created, and then setting the value of the dt so that on return is dt will actually contain the values that I've got that have been set in here. So that's where I've passed it. And down here notice I'm just showing off again use of this serial streaming method. Serial greater than, so it prints out DOM equals, then DOM day of month, which is that value up there, month, MNth, year, and so on. And then so essentially it's just showing how I can actually print out. And notice that would take 2 or 3 serial dot prints. So there's my parse RTC in buffer. Now, first thing that I need to do within the loop function here is to realize is that I'm going to have delays. Now those delays I can't really control particularly much. Some I can control, some I can't. The ones I can't control, for example, is I'm looking at a serial stream and I'm looking to see whether or not someone has either typed in or my PC has sent up a string that says reset the clock. And I just don't know if there's anything within that stream. If I see a command that says that, I have to act on it. But that means then if there's not a command, I'm going to have to wait a certain time to make sure that there's not one, and then time out, or if there is one, to act. So I never know just how long it will take how long to take, basically, because each of these things take a delay. Also as well, if the time hour changes, I'm going to get beeps, and beeps, I've got them in just using simple delays at the moment, so delays will change depending on how many beeps there are. So essentially that can all be rather complicated, but I really want to set a stop clock and say is at the beginning start a stop clock with the millies command, and this runs automatically, and then down here it basically says stop at stop clock. So within here is where all I can get by delays, so at the end of it I can actually work out how long was the actual delay, because what I want to happen is when it prints out, I don't want it to print out any faster than every say 5 seconds or whatever the print time interval is. So this will allow me to compensate for how long it's been stopped, so that for example down here where I do a delay, that's 5,000, I had it with globals, and the total delay time is something to do with how long I've just spent in measuring it. So let's continue from that one. So start a stop clock, then I check for time reset. Now what will then happen is I have a function here which I'll look at in a second. It essentially looks at the serial stream and says, do I have a string formatted in a certain way? If I do, then I need you to extract the information it says to be, and then update the time within here, and then update the values of that time. Here I create a buffer of 20 characters. That's 19 for this information that we're going to print out to the monitor, plus the extra one for the 0 at the end of a series of characters to denote the end of a string. And then send that to a function called dtBufferInit, and what that does is I pass all this information to that buffer, and all this is really doing is saying is if it was the first of the month, it would make sure is that it uses all 1 there rather than just 1. So essentially it's making the format of this output that's going to go on the monitor, that's going to make it be the same as the input that we expect. So a properly formatted string. Here I'm doing serial print ln dn dtbuff, nothing to stop me, just doing serial less than, and then just have typed dtbuff in there. Here essentially is what I'm doing is I'm checking to see whatever value is stored in current hours 24, and if it's not equal to the current hours at the moment, it means the hours have changed, so I'm now going to get chimes. And I've got this line here, calls a function called get chimes, and essentially I'm sending the hours to it, and this basically actually does, although I've saved that value of chimes there, I'm not using it. Get chimes is actually doing all the banging and noises itself, noises and flashes itself, and then I'm resetting the current hour 24, so an hour later it should change. Now I'm saying is, alright, you've got all that stuff, stop the stop clock, and then create a variable called total delay time. And here what this basically says is, because millies is an unsigned long, is it means it can have any value up to 4 billion odd, which even at 1,000 a second still takes a long time to fall over and get out of it and roll over. It takes about 7 weeks of non-stop running for millies to overflow. So what this line here does, very unlikely, but it's my attempt to just try and fix it if it did happen. I've not tested it, by the way, as it would just take too long. I think it's probably right, I'm hoping it's right, but it seems to work, and if it doesn't roll over, so I'm just taking it at faith. I'm sure you'll tell me differently. So this basically says if the end time is less than the start time, the only way that could actually happen was if it rolled over. So what I then do is I find out how far from the top were you and subtract it from there, so that'll tell me basically how long it ran for from the start time up here to the time that it overflowed, and then I can then add that time on to what the start time is. So essentially it's looking at the end and adding it to the beginning. So now I've got the total delay time. However, 99 times 100 or 49 days over 7 weeks is it's going to not be overrun. So it just simply has the end time minus the start time, convert it to an int, because I've said here is that this total time is an int. Total delay time is an int. so I'm just casting it to an integer. And then what I'm doing here is, this is basically saying is, now I want to do this every 5 seconds, but it's possible that your total delay time is greater than 5 seconds, so I want you to print that out, because that basically is going to start screwing up the code, and we'd probably want to do other bits and pieces as well. And then I run that delay, so that delay will run for whatever was left of my 5 second between prints, and that would seem to work okay. Your problem comes because the delay actually blocks things. Your problem comes is if the delays start to over impinge that interval. If I want 1 second, I have to be a lot more careful. I'd have to consider about whether I want chimes or not. Right, so now we'll look at 3 other functions. These essentially is the buffer init and 2 functions which help it, dt buffer init, do its job. And we saw dt buffer init there. dt buffer init, its job is to take a series of values, day, month, year, etc., and put them into a format which is recognizable and consistent for the rest of the program. So dt buffer init has a pointer to a buff, then it has the values for the individual elements of that buffer, and essentially here what I've got is, I'm saying is ret year, which is a pointer to a character, is equal to pad_int of year. Now what I'm doing here is I'm setting the value of year, let's say it's 2119, and that then goes into here. This receives I then as 2119, and it returns a pointer to a character. So what I've got here is, first of all, is I'm just creating a static buffer of characters. Now the reason I'm using static here is if I didn't use static, then when this function finishes, is the value would be on a stack and it wouldn't be accessible outside the program. So making it static means it persists for longer than the lifetime of that function. I'm not going to go into huge detail on that, as the video is already getting quite long, but you can try it yourself, try replacing, removing the static and keeping the static and so on. So essentially is, this sets up to be 5 characters, and that putting a value there just gives it, make sure it's got a 0 at the end, just for laziness really. Then I'm converting, and what I'm basically doing is I'm adding to that buffer C. I'm starting with that buffer C. The address at the start of the buffer is, I'm saying is, take the value of I and make it into a decimal integer. So it takes an integer and makes it 1856, so that the characters 1, 8, 5, 6 appear, and a 0 appear in the C, and that C is returned. So that by the time I get back to here, it means is that I'm doing my pad_int, and ret year is a pointer to it. So it's pointing at something that's actually real. If I didn't have the static there would be nothing to point at, and it would error out. And I do that really, just all I'm really doing is making sure is that the string is properly formatted. So you can see here I've got like 2 forward slashes, which makes 1 forward slash, which is the divider between let's say the day, the month and the year, and then the colons to have between the hours, the minutes and the seconds. So essentially this, in conjunction with these, just helps us make a well formatted string. Now we come to probably the most important function as far as the clock's concerned, about setting and resetting the time. This void check for time reset. It's called from the main loop, and it checks basically to find out whether or not we just carry on printing the timer or whether or not we actually change the time. And it does that by keeping on looking at the serial input stream. And here we can see on this is like a screenshot from the monitor showing us that the value has been printed out within the main loop, and notices that each reading is 5 seconds apart. That's the value we demanded from the program. Now if, for argument's sake, I type in the string of characters in here, this is going to be interpreted when I press the send button. It's going to be received by this check for time reset, and hopefully it will then look and says, that is a request to change the time, I'll change the time. And here we can see down here is, if I did press the send, what the response from the monitor would be. It basically first of all passes those values and takes the X out, and it passes those values and it carries on printing out the actual time. Again, 5 seconds difference as before, no change there. And this code is the code that does it all. Now
First of all, is I'm setting a length of 23, which is like the number of characters. If I read that many characters and nothing's happened, then that's definitely a kind of upper limit. Here I've set a timer on the serial for 500 milliseconds as opposed to the default of 1000 milliseconds. I've created a buffer that will hold a value like that exactly, plus the terminating actual 0 on it. Notice is that any value is that the terminating character X is not included there, because this read bytes until actually doesn't put the terminating character in. It puts it up to, but not including the terminating character. So essentially is number of bytes then at the end should be exactly the same as here, which is 21. Notice we're not counting the extra 0 here, but we do need it for the buffer. So if it reads 21 bytes, that means it's read the X and it's done all the whole stuff here. And the first thing I do then is I put a couple of quick beeps in just to show that it's actually changed. Then down here, create a variable dt. Just for the moment, this dt basically is so that says please pass that string that I've got within that buffer there now and extract from it the different elements of the date and time, and then set them according to what value. So by the end of this function here, we have reset the real-time clock. Right, get chimes is about the last function we have in our program, and it's essentially called when our loop detects is that the hour is different from the hour, the current hour is different from the last hour that did chimes. So we send basically like 12 for example, and we create a variable called chimes, type byte, and it's basically saying that if the input value is 0, then we have 12 chimes, fair enough. Otherwise, if the value we send is greater than 0 and it's less than 13, then we just take the chime straight off. So essentially it's just making sure is that we don't end up with more than 12 chimes and we get the right number. So that's all this code does. And then here we're just running a very simple for loop up to the number of chimes, and all it's doing is putting the light on, putting the buzzer on for a period, then putting the light off, the buzzer off for a period, and it will do that the number of times. Now as it's doing this, because it's using delay, it does mean it's blocking, and that blocking does mean is that nothing else is happening. There are better ways, but at the moment we'll just take that and we'll handle whatever problems we get, which is what I did for example with the setting the timers using the millisecond within the loop, and then it returns chimes. In the program it's not actually using the return value because this does all the work here. So that's the get chimes. Now we're getting towards the end here, and this is showing basically using a C# program in Visual Studio, and it's a C# monitor console program, and it uses basically two things here, system and system.io ports, and the program is all contained within main. If you don't understand C#, then blank out for this, but it is a useful technique, and if you use other languages it should be easily modifiable. So essentially I've created serial port SP, I've set that up to a new serial port, made it COM3 the same as in my Arduino sketch, my Arduino is using a baud rate 9600 and a read timer at 10,000 because it's got read timer of 10,000 milliseconds or 10 seconds. It's just that if there's a gap between me running this program while the Arduino is switched on but not putting anything out, then it will time out. But it's important before we run this program to make sure is that our serial monitor is closed with the Arduino, because essentially what we'll be doing is when we're running this we won't be able to run the COM port, the serial monitor in the Arduino. Instead we'll be using this instead to see what we need to see. And essentially then what it's doing is opening the serial port, it's setting a variable x equals 0, and then while true means forever, it basically is reading from the serial port, and what it'll be reading will be the stuff that would normally get sent to the serial port of the Arduino, except of course it comes out here. So we're seeing what we're seeing here is here what would be on the serial port, except we're seeing it on our console here. And this level is that every time it clocks up to 5,
See here, once it gets clocks up 5 times here, it then gets the actual date and time that we have within the program, and it extracts to it along with the important text at the end. It sends that string up to the serial monitor. So here it's doing an out, so it's outputting a string to the serial monitor every 5 loops or so of the program. Every 5 loops, so it just doesn't bombard the Arduino with more strings than it can handle, or more requests to change the time it handles. So every 5 loops it will redo its work. So basically it's grabbing the stuff from the Arduino by the read line, and the timeout is just there to make sure is that if the Arduino is not doing anything, it's going to have to wait 10 seconds before it actually stops the program. So that's it, grabbing it, printing it out on the monitor, and there we run through. And it's important to keep the serial monitor off while this program is running. And do remember to comment or uncomment in the program the hash define set RTC and startup, because essentially it is, once we've actually set up the time running this program, we probably don't want to have in our startup routine, we don't want to keep resetting the time. So that means we comment it out, but that was mentioned in the video. Now, hopefully you've understood all this. I mean, obviously you can get the program and look at the code and try and look at my explanation. Hope it makes sense. And when it does make sense, then my plan for my next video is going to be actually adding an LCD 16:2 display on, and displaying the time and date on this LCD, which I think is quite a bit handy. It makes it more like a portable clock or something. Anyway, thanks for just now, and bye.